Hello everyone, I am Monika Bhushan and today we are starting lecture number 14 of partial differential equation. In today's class we are going to derive one-dimensional wave equation, okay? And in next class we are going to see the solution of one-dimensional wave equation, fine? So but today's class we will be stick with the derivation only. So to start the derivation of one-dimensional wave equation, we will first assume some scenario where we can see this wave equation, okay? So very common example could be vibration in a guitar string, okay? So that means if you just imagine that the guitar which you play, where what happens, the string is present, fine? So the string is elastic, is flexible by nature, fine? And this is tied both sides, okay? And then this you have actually stretched this string, right? This shows that the string has tension in it. All over the string we can see the tension is present, okay? And you can see the thickness also is same, is uniform all over the string. So if you will plug the string of your guitar, so what will happen? Then you will see that the guitar string will start vibrating, okay? So the vibration will not be very high, it will be somewhat like this, okay? So this way you will see the string is actually vibrating. So this is one perfect example of one dimensional wave equation, okay? So a wave is actually advancing in horizontal direction, but the to and fro motion, the motion is actually happening in the perpendicular direction of whatever the direction it is advancing. So what we have seen here is nothing but the vibration in the string. So if I will give you another example, that could be ripple on the surface of water. If you will throw a light object on the surface of water, then you will find that the motion will be again, it will be happening in the perpendicular direction, but the wave will be advancing on the surface of water, correct? No. So this is another good example of one dimensional wave, fine? So to start with the derivation of this one dimensional wave equation, we will consider some assumptions so that a scenario will actually show all those properties of our one dimensional wave equation, fine? So here are some assumptions listed. So what these assumptions say us, that string which we are going to use for derivation of our one dimensional wave equation, so the string should be flexible, fine? The string should not be very rigid, okay? So it should be flexible or elastic by nature, so that we can see that the wave is actually happening, fine? Another assumption is the wave is due to transverse vibration of stretched string. Okay, what does it mean? Transverse vibration is what? So this is the kind of vibration where the element moves to and fro in the direction perpendicular to the direction of advance of the wave. That means what the example we have given, if you are throwing some lightweight object on the surface of water, so what is happening? So wave is actually advancing on this horizontal, on the surface of the water, but actually the motion is happening to and fro perpendicular, right? So this is called as transverse vibration. Same transverse vibration we see in the string of guitar. When you plug the string of guitar, so same thing you can see, right? So the motion is actually happening to and fro perpendicular direction of the horizontal of the direction where the wave is advancing. So this is only called as transverse vibration of stretched string. Here we are saying stretched string, that means what? The string is actually having tension in it, fine? Okay, so the third assumption is what? Mass per unit length, that is rho, is constant. Okay, what does it mean? Why we are taking mass per unit length? So the string we are taking consideration, so string has some length on it, okay? So string is having some, suppose we'll say that it has length L, so this mass of this string is actually uniformly distributed all over the length of the string. So that means if we will consider the mass per unit length, some chunk of your string, same mass will be present, the same mass will be present even in this area and so on, fine? So this is called as mass per unit length, and this we represent with rho. So this will be constant throughout the string, fine? So this is our another assumption. Now we are going to consider the fourth assumption. Here it says that the effect of gravity can be ignored due to large tension in it. Fine. We know that the string is stretched. Fine. That means the string is showing tension. The tension is high in the string, and the gravitational force, of course the gravitational force will be present even you are plucking the string in horizontal direction or vertical direction, whichever way you are keeping your guitar. Gravitational force will be present, but we are ignoring that gravitational force because the string which we are taking consideration for our experiment will be having large tension in it. Okay, so we are just considering the gravitational force negligible, so we are ignoring the gravitational force. Fine. Now the fifth assumption says that string shows negligible deflection in x direction. Okay, what does it mean? So the same thing what we are saying here, that the string, if we have plucked the string of guitar, so what is happening, we can see the deflection is present, the small deflection is present, but the deflection is actually perpendicular to the x-axis. That means the motion is actually happening to and fro in the perpendicular direction, in the y direction. Fine. We are not considering the deflection in the x direction. In x axis we are not considering the deflection. It will be very negligible. And the last assumption which we are going to discuss is the string shows small deflection in y direction, right? Keep on saying that deflection will be present but in the y direction only. But what we are saying here, the deflection will be small. Deflection will be small in y direction. Indirectly we are saying that the slope will be very small. Okay, so slope at particular point will be very small. So this is another assumption which we are going to make. Fine. This is very important. Actually we will be discussing what does it mean. Fine. Now we are going to see actually what is happening in the vibration, okay, in the wave. So what so if I say that here is the diagram where I'm just writing down, this is the deflection in the y direction. Okay, this is your y direction, this is your x direction, and what happens that this is something we can see that some small deflection is happening in my y direction. The deflection we are actually denoting with u. Fine. And this is your x direction where the length of the string we can say that this is L. Fine. So here if we will just, because we have to derive the equation that what force is actually happening in my x direction, in my y direction, for that what we'll be taking, we are just going to take two small points on this string. Suppose names I have given as A and B. So here we will be actually dealing with the force, the tension at these 2 points. So this point what I have taken at A, this is actually having distance x from your origin, and here you will find that the point B is actually x plus delta x, very small distance delta x apart from A. That means the distance between A and B is very small. This is something which is delta x. Fine. So same thing we have drawn here in enlarged form. So what is happening here? We have said that this is nothing but this is the deflection, okay, in the string, in the y direction. Deflection we are saying as u. Fine. And this is the length. Fine. And this is your x axis, and here you can see that this is your y axis. Fine. So those things we have just now discussed. Now we are just we have taken these 2 points A and B. So these 2 points A and B are present here. Now we are going to discuss the force which is actually present on this point A and on this point B. So the force is what? The force is tension, because we know that the string is stretched. Fine. That means at each and every point of this string the tension is present. Fine. So here at this point A, we have just given this direction of this tension. The tension will be in the downward direction. Fine. So this T1 we have given the name. Fine. Now at this point B, what is happening here? Again we can see that at this point the string is having tension. The force is there and the tension is upward. Okay. Fine. So now if the tension T1 and T2, two forces we have taken, so now we are going to discuss the component of the force T1 and T2 in horizontal direction as well as vertical direction. Fine. And again, why we have taken this tension? Because if this string is actually vibrating, so this force is present, correct? No, force is present. Basically we are saying that the deflection is present in your y direction. Force is actually causing the deflection. That force only we are going to analyze. Okay, so at any point if you are going to take the force, so we have just taken 2 points A, B, where the force, that is tension, is actually applied. Fine. So we have taken these 2 points. So this is T1 and this is T2. I'm going to find the horizontal component, okay, and the vertical component of this tension T1. Similarly, for this tension T2, I'm going to see what is the horizontal component and what will be the vertical component. Fine. No, we have written down the same thing. T1 is tension at point A and T2 is tension at point B, and basically the tension is present all over the point. Fine. We have said that the deflection which is caused by this force, which is caused by this tension in horizontal direction, is negligible. Fine. We have said that in horizontal direction there is no deflection. That means we are going to say that the T1 force which is present in that horizontal direction and the component of T2 force which is present in horizontal direction will be same. Fine. That means what we are saying, since the deflection in horizontal direction is negligible, so we will be saying that at any point the horizontal component of the force will be same. Fine. So we are going to say that the horizontal component of T1 is nothing but T1 cos alpha. These things we know, we have studied in mechanics, that the horizontal component here in T1 will be T1 cos alpha, and for T2 the horizontal component of T2 force is how much? T2 cos beta. We are going to write T1 cos alpha is T2 cos beta. Fine. So what we had discussed, that in point number 6, that the deflection in y direction is very small. Right now we are saying that the deflection in horizontal direction is negligible, but in y direction the deflection is present, but this is very small, and this small deflection actually says us that the slope is very small. That means the angle which it is making is very small. Okay, since the angle is very small, alpha or beta, we know that cos very less angle, that means nearly 0, cos 0 degree is 1. Fine. No, so that means if alpha and beta are very small, so we will treat them as 1 only. Fine. So we are going to say that this is T1 into 1 equals T2 into 1. Fine. That means tension which is present at point A is same as tension which is present at point B, and we'll just give the name as T only. So fine. So this is the reason we say that tension in the string is same, because the slope is very less, very small slope is present. So the smaller value of cos is actually nearly 1. So we'll say that the tension in the string is same. Okay, now we will discuss what is happening with the vertical component of T1 and T2. Fine. We are comparing the vertical component of forces. So we'll see that, so T2 sine beta. Fine. So T2 sine beta in vertically upward direction, and this is your vertical downward direction, T1 sine alpha. So vertical direction downward, so I'm writing down minus. So this is your T1 sine alpha. So two forces we can see. Now this T2 sine beta minus T1 sine alpha is nothing but the force which is applied on this string. And what is the force? By Newton's second law, we know that force is nothing but mass into acceleration. We are writing mass into acceleration. Okay, so what is mass into acceleration here? So we'll say that again, the mass which we are considering here at this point, right, between this x and x plus delta x, what is the mass? We have said that in assumption that mass is actually uniformly located throughout the string. Okay, So we have considered that mass per unit length, that is rho, throughout the string is constant. Fine. So we have to here write down mass into acceleration. So mass will be how much? It will be rho into delta x. Fine. Why I'm writing delta x? Because rho is what? Rho is mass per unit length. And I have to write down here mass. So it will be your rho into delta x. Okay. Now multiplied with acceleration. So acceleration is what? So this is second derivative of the deflection, right? What is acceleration? If this u is present, right? U is what? This is the deflection in your vertical direction, fine. And we are saying that there is no deflection in horizontal direction. So the acceleration will be how much? Acceleration will be del by del t of u. Fine, no? That means we can write down here, this is nothing but del 2 u by del t square. So, and what is u? U is deflection. Fine, no? So this is deflection in y direction. So here I am writing del 2 u by del t square. Fine. Now what I am going to do, I am going to divide the left hand side, even the right hand side by t, okay, by tension. Okay, so in that case what will happen? My left hand side will become t2 by t, okay, and then this is your sine beta, and then this is your t1 sine alpha divided by t. Fine, my left hand side I am writing down, and here I am replacing this t with, in my first term I am replacing t with my t2 cos beta. So it will happen what? It is nothing but t2 sine beta divided by t1 divided by t2 cos beta. Okay, and this is your t1 sine alpha, and then this is, instead of t I am writing down t1 cos alpha. So t1 cos alpha. And why I am writing down? Because I am taking help of this equation number 1. Okay. So in this case what will happen? T2 and this T1 gets cancelled, and left hand side shows you that tan beta, okay, tan beta minus tan alpha. So left hand side is nothing but tan beta minus tan alpha, and right hand side is rho into del x by t into del 2 u by del t square. Okay, so if you will focus on my left hand side, what does it mean? This is saying us this is tan beta minus tan alpha. That means the difference between slope at point B, okay, and point A. That means what is my tan beta and what is my tan alpha? We know that tan alpha is nothing but the slope string at point A. Similarly, what is my tan beta? Tan beta is the slope of this string at point B. Okay, and here my left hand side says that this is tan beta minus tan alpha. That means difference of slope between points B and A, and the length of B and A is nothing but this is your delta x. Fine, no? So if we will see, yeah, we have done till here, we have got till here. Fine, no? This is tan beta minus tan alpha is my rho by t delta x del 2 u by del t square. And we can do one more thing, dividing delta x in my left hand side also, right hand side also. Right hand side the delta x will get cancelled. Left hand side is again what it is saying us, this tan beta minus tan alpha divided by delta x, where delta x is very small, correct? No, this is delta x, will say that delta x tends to 0. If we are taking limit where delta x tends to 0, then what does it mean? This left hand side says us that this is again rate of change of slope at point B and at point A. Fine. So what is the slope at point B? The slope at point B will be, I am writing down here, del by del x of u at the point where the distance from the origin is x plus delta x. Fine, no? So this is the slope. Okay. Similarly, tan alpha is what? Tan alpha is at point x. What is the rate of change of this deflection? So u is nothing but the deflection. That means we are talking about the slope at point A. Fine. Now the equation number 2, what we have seen, we have replaced tan beta with this term and tan alpha with this term. Okay. Now we are dividing throughout with my delta x, and delta x, we know that this is very small, the distance between a and b is very small. So this complete thing says us that we are going to find again del by del x of the difference between slope. That means we can write down this left term as del 2u by del x square. So del 2u by del x square is, the right hand side is as it is. This is my rho by t, and then del 2u by del t square. Fine. Now we can write down this in this way. That means I'm just rearranging this equation. I'm taking that del 2u by del t square will be how much? This is nothing but it will be t by rho, correct? No, this is my t by rho, and then del 2u by del x square is coming into my right hand side. Fine. Now, now what we can say that this t by rho will always be some positive quantity only. Why? Because tension at any time we are considering is positive, and the rho, that means nothing but my mass per unit length will always be positive. Okay, so taking tension and rho as positive, instead of writing t by rho, we are just replacing with some other value, suppose c square. Okay, so why we are writing down c square? Just to show that this is positive. Even some value might, if you are putting c as minus 3 4 5 something, the square will always be positive. So just to make sure that this quantity will always be positive, we are just replacing it with c square. So that means we are writing down del 2u by del t square equals c square, something positive quantity. Along with that, this is del 2u by del x square. Either you write in this fashion or you write utt, because this is your del t square. So utt equals c square uxx, and this is only the wave equation in one dimension. Fine. So we have derived this equation, and in the next class we are going to find the solution of one dimensional wave equation. Fine. So if you find this class useful, please like and subscribe my channel. Thank you.